Okay, we're on climate pattern factors, which is objective 12. We're going to discuss all of the different factors that influence the climate. So you can pause it and copy down tomorrow's date and objective number 12. You can see on this slide all of the different factors that are listed that do have an influence on the climate of an area. You don't need to copy these down because they are in your note packet, numbered with latitude being number 1. And as you go through pages 10, 11, and 12, you'll see each of these factors listed. So latitude is number 1, meaning it is the most important factor. We've already discussed numerous times in class how latitude influences the temperature. So if you have a low latitude, meaning you're near the equator, you're going to be warmer. If you're high latitude near the poles, your temperature tends to be cooler, and it varies a greater deal. So then you say, well, why are the poles so cold? Well, I showed an example in class when we were using the flashlight to talk about the North Pole and how in summertime it has 24 hours of daylight, but yet it's not wicked hot there. And you would say that's because the angle is so low. So if you look at the slide, you can say one reason the poles are cold is they have lower average angle of insolation. Okay? And on average, they have less insolation as well. So it tends to be cooler there. So when we talk about latitude and we talk about the temperature range, we see that there is a direct relationship. The further you get away from the equator, the greater the temperature range. Whereas at the equator, the temperature tends to stay more flatline, more of the same. It's always warm at the equator. They don't get really cold temperatures, so it tends to stay closer to be constant. Whereas far away from the poles, or towards the poles, you're going to get a bigger difference. What is the relationship between the average temperature and the latitude? Well, as you are near the equator, it's always going to be hot. When you move away from the equator, it tends to get cooler on average. Yes, they have warm summers, but they're going to have cooler winters. So on average, the temperature is less. So that is an inverse relationship. Right? You can think of it as going away from the equator, your latitude is increasing, thumb up. Temperature tends to cool, thumb down. Factor number 2 is the altitude of the elevation. If you live on a mountain, you have a different kind of climate. Right? Lower elevations near the bottom of the mountain tend to be more stable. They tend to not have such vast temperature changes and moisture changes, whereas if you're at the top of the mountain, things tend to change very quickly. So what we can see here on this slide is as your altitude up a mountain increases, you tend to get cooler. It's colder up at the top of the mountain. That's why if you look at this picture, it's got snow caps up at the top. And you generally tend to get more precipitation. It's colder and wetter at the top of the mountain. Factor number 3. This is similar to lab that we just completed, right, where we were analyzing Phoenix and LA, Bismarck, North Dakota, and New York City. Here is a different graph comparing Vancouver and Winnipeg. And if you look at the location of them, you can see Vancouver is the red line. And if you look at the map, you can see that Vancouver is the red dot, so it is over by the water. Winnipeg is more inline, so it is the blue dot, and you can see the blue line. So when you compare their temperature ranges, you can see that Winnipeg has a much larger temperature range. It's very similar to the one in the lab with Bismarck, North Dakota. So you can see how Winnipeg has much colder winters. I can circle that in green, okay, or over here in December. Its winters are much colder, but then you can see it does get really warm summers as well. So there's a huge temperature change. Whereas Vancouver, and I can circle this as well, their winters are warmer because they're near the warmer water, and it takes water a long time to cool down. Right? But in summertime, their top point, their summer is not as warm, right? Because they're near the cool water. So in summertime, the cool water keeps them cooler. In wintertime, the warm water keeps them warmer. Right? And it all has to do with that large specific heat of water. So marine climates, what does marine mean? Along the coast, near the water. You can see they have small temperature ranges, cooler summers and warmer winters. So this picture here would be an example of a marine climate, kind of like they were showing Winnipeg, or you had LA or New York City in your lab, although this picture does not look like LA or New York City. Continental climates, that's like Bismarck, North Dakota, or they just showed Winnipeg. In the lab they also had Phoenix, although I guess this doesn't quite look like Phoenix. They have larger temperature ranges. Their summers are hotter and their winters are colder. Factor number 4, ocean currents. If you look at your reference tables and you look at the map of the ocean currents and then we look at global winds, we see that there's a connection between them. Right? It's the winds that create those surface currents on the edge, right? And the currents under in the water are really like huge rivers of water. And we had talked about Finding Nemo already with Crush, and when he was in the EAC, that big current of water, you get in that and then it's just pushing you along. The water is moving very quickly. So if I go to page 4 of my reference tables, you can see this is the surface ocean currents, and what we had said about this is that you could see in the northern hemisphere, because of the Coriolis effect, they are all curving clockwise, but in the southern hemisphere they all curve counterclockwise. And remember that on page 4 of the reference tables, the key is there on the bottom right, showing you what the warm currents and the cool currents look like. So again, it's the Coriolis effect that causes these clockwise and counterclockwise currents, and these large currents that circulate are called gyres. And you can see on the map the North Atlantic gyre and the South Atlantic. You can see that they're going different ways, clockwise, counterclockwise. Currents depend on the temperature in which they're passing through. So if the current is coming from the equator and moving north, like I will say this one right here that I'll put green, then that's going to be a warm current. It's coming from the equator, bringing all that warm energy up towards the north. But then if you have another current, like this blue one that's coming from the poles and coming down, right, that is going to be a cold current because it's bringing the cold water from the poles down to the equator. So the currents are the way to kind of balance out the solar energy. They help balance out the warm and the cold. And if you happen to be living near one of those, if you live near a warm current, your temperatures, your climate tends to be a little bit warmer. Right? But if you're near a cooler current, you tend to have cooler climate. And the example that I used, and I'll mark with black X, is if you go surfing, and I talked about a friend of mine who goes surfing on the East Coast, so that black X, I'll circle it, right? That's the warm Gulf current. So the water is not as cold to go surfing. But if you go out in California current, right there, that black X, it would be colder water because of the different currents in the temperature water that they're bringing near the beach. Factor number 5 is El Nino. Right? El Nino has to do with the trade winds in the Pacific Ocean and how they want to go from the east to the west, right, towards low pressure that is near Australia. So that's what that diagram is kind of showing you, how you get normal conditions, and the trade winds in this particular picture are going towards the left, going towards Australia from South America. Well, as that happens, what happens with the currents along the winds is that you get cold water coming up along South America, and it's coming up from deep. And I'll mark that red in the picture. That's called upwelling. What that does is it brings that cold water, right, from deep under in the bottom of the ocean, brings that up, and that brings nutrients, right, which sustains the ecosystem off of South America. So when the upwelling brings nutrients, that brings little fish, which brings big fish, and fishing for the people that live along the coast of South America. Well, in El Nino, what happens is the ocean flow reverses direction, right? So you don't get a lot of upwelling. So now the surface currents carry the nutrients away from the coast. Right? So you can now see in the picture the weaker trade winds. So you do not get a lot of upwelling. So it's kind of weaker right there at that red X. So therefore, you don't get a lot of nutrients. You don't get a lot of fish. So during an El Nino, the folks in South America are not happy because they have a hard time catching fish. And the reason for that is you have warmer ocean temperatures, which increases evaporation. And if the water is warmer and you get lots of evaporation, it creates a lot of humidity and moisture. You get a lot of clouds. You get a lot of rain. Right? That influences the wind patterns in the jet stream, like we talked about in weather, and it totally changes what weather these people are used to along the coast of South America and even in North America. So it's bad enough that they don't get fish, right? But instead they get lots of rain, lots of clouds. So during an El Nino season, people in California and South America tend to get mudslides, flooding, heavy rains. And us in the Northeast, our wind patterns change, weather changes, and we've had some really bad ice storms during El Nino conditions. Folks in the Southeast tend to get more tornadoes during an El Nino, all because of the temperatures in the Pacific and how it shifts the weather and the wind patterns. La Nina is the exact opposite. El Nino is the little boy, La Nina is the little girl in Spanish. So La Nina is the exact opposite. Now you get really strong trade winds. So what that does is it creates really strong upwelling right at the red X. That pushes that cold water right across the Pacific Ocean. So yeah, the folks in South America might get a lot of fish, but what they see now is from that X, you get all this cold water getting pushed across really strongly across the Pacific, and it changes the temperature of the Pacific Ocean. So now if the water is colder, you're going to get less evaporation, you get less moisture and humidity above the ocean, so you get less clouds, so you get less rainfall. So a La Nina means more of a drought for California and South America. Exact opposite weather of El Nino. This is just a map showing the United States with jet streams, the purple and the red arrows, coming off of the Pacific Ocean. And you can see how during El Nino and La Nina over the Pacific Ocean, you get different temperatures, which means you get different pressure systems, and it changes the way the jet stream shifts, which changes the weather patterns. And last but not least, factor number 6. Actually, no, we got 6 and 7. Factor number 6, mountain barriers. We've discussed this already in weather, how the orographic effect, mountains can block the weather, create what we call the rain shadow, so that you end up with an interruption in the normal path of the weather and the wind belts. What happens is when you have a mountain barrier there, you have the windward side is the side that the wind is hitting. That forces the air up the mountain. And as it goes up, we've discussed this in weather, how it cools. If it cools to the dew point, that's going to form clouds and precipitation. So on the windward side, you get clouds, you get snow or rain, depending on the temperature. Now as the wind brings the air down on the other side, they call that the leeward side of the mountain. That's the side that is away from the prevailing wind. Now as it comes down, that air can get compressed due to higher pressure, so that warms it up, and that tends to move it away from the dew point, so it is drier. So you get opposite types of weather on either side of the mountain. This is just a shot of looking at the mountains far in the distance, and you can see there are clouds near the mountain, but there's blue skies away from it. So you can kind of tell that those clouds are being formed only near the mountain, where that air is being forced up over the mountain and cooling to the dew point. A really funky type of orographic effect is the lenticular clouds, which form as air is being pushed up and it spirals up as it's going over the mountain, and it forms like a spiral-shaped cloud. These photos here are genuine clouds. They are not photoshopped, but they are a unique, funky type of formation. So now what I want you to do is I want you to pause and see if you understand the difference between the windward and leeward side of the mountains. I want you to look at the 4 questions that are in your note packet and see if you can answer them using the words leeward or windward. You can pause it, answer those questions, and then play when you are done. And here is now the final factor, number 7, the wind belts, which again we already did a lab with this, right? But it does influence the weather, the climate over a long period of time. So remember, as we're talking about climate here, we keep talking about weather, but it's just over a large period of time. And the wind belts have a huge effect on that. Page 14 is the diagram of the wind belts that you have used a few times already. And remember, if the prevailing wind is coming across water, that's going to pick up the moisture from evaporation, which means that it will be more humid, and that's going to bring precipitation, either rain or snow. And when that happens near us, we call that lake effect. So you can look at the picture on the left, and you can see all of the blue bands from the radar that are showing the lake effect coming off of the lake. So if you look here at the Great Lakes, and then you can see the precipitation on the windward side. You can see precipitation coming off the windward side. If you look at Lake Erie and Lake Ontario, again, you can see all this coming off of Lake Ontario. See all this coming off of Lake Erie. So you can see examples of lake effect in the diagram. If the prevailing wind is coming off of a continent, it will be the exact opposite. It's going to bring dry air. It's not picking up moisture. Okay. And then we also discussed back with winds, if it is a tropical wind, it's coming from lower latitudes, so it brings warm air, and polar winds are coming from closer to the poles, so they bring colder air. So that influences your climate, depending on what wind belt you are near. So that concludes the 7 factors that influence climate. Hopefully now you have Unit 7 notes all completed.